Hi everyone, I'm Luisa Borsato. I'm a PhD student at the University of São Paulo under the supervision of Rodrigo Bizacco. And today I'm going to talk about the Bruching-Lanfurel theorem for irreducible Sohc shifts. So before starting, I would like to thank the organizers that made this event possible. The work I'll present here is a joint work with Sophie MacDonald, who is a PhD student at the University of British Columbia, and we are very grateful to Brian Marcus and Tom Mayerovich for their support throughout this work. So in this talk, I'm going to present to you two definitions of a Gibbs measure on subshifts that are equivalent, some preservation of Gibbsinness results, and finally, a Bruching and a Lanfurel theorem for irreducible Sohc shifts on Z. Before proceeding, I would like to say that after finishing this project and after submitting the abstract for this Congress, we became aware of the work of Viviane Baladi, who in 1991 proved a Bruching and a Lanfurel theorem for finitely presented dynamical systems of which Sohc shifts are a particular case. So some of the results I'll present here were already proven in the literature. So let's start with some framework. We consider a finite alphabet, a countable group, G, the product topology on the full shift, the shift action of G on the full shift, which is here given by the right action. And when the group is the set of the integers, we have this widely known presentation of the shift action. A subshift is any closed and shift invariant subset of the full shift, and a special class of subshifts is the class of shifts of finite type, which are shifts that can be obtained by forbidding finitely many finite patterns from the full shift. All measures we're going to consider here are G-invariant Borel probability measures. So now let's answer the questions, what is a Gibbs measure? So before that, we need to consider a sequence of finite sets that exhausts G. And given that, we define the subrelations by this. So X and X, the pair X and X prime is in the subrelation T Xn if and only if X and X prime coincide outside lambda n. And then we define the Gibbs relation as the union of these subrelations. A co-cycle is a measurable function from the Gibbs relation to R that satisfies this equality. Now the first definition of a Gibbs measure I would like to present is what is a DLR measure. So a DLR measure is a measure that satisfies this equation right here, which is about the conditional measure of any Borel subset given what we know that happens outside a finite set lambda. The second definition of a Gibbs measure I'd like to present is the definition of a conformal measure, and for that we need to say what a holonomy is. So a holonomy is a Borel isomorphism between two any Borel sets A and B, such that this pair is in the Gibbs relation. And a measure is conformal if we have this expression right here for the Rodon-Nikodym derivative. Before proceeding, I would like to present a special class of potentials known as potentials that have dissummable variation. So we restrict ourselves to when the group is ZD. So for a continuous function f and for hk greater than 0, we have the kth variation of f, which is how much f can differ if x and y coincide inside lambda k. And then, given that, we can define the SVD norm, which is the sum. And when the sum converges, we say that the potential has this summable variation. So now talking about the equivalence of these two definitions, the first result we have here is by Keller. We can find this result in his book from 1998, which says that for the full shift and a potential with this summable variation, a measure is conformal if and only if it satisfies the DLR equations. And more recently, Kimura proved that for any subshift on ZT and any SVT potential, a measure is conformal, then it satisfies the DLR equations. And conversely, if a measure satisfies the DLR equations, then it's topologically Gibbs, which is a weaker concept, and it was introduced by Meyerovich in 2013. And more recently, we have proven that a measure that satisfies the DLR equations is conformal for any countable group, any subshift, and any cocycle. The equivalence here is important for us because the Dobrushin and Lanfrewell theorems were originally stated for the DLR equations. So, and what we prove here, for us to prove the Sohc, Dobrushin, and Lanfrewell theorems, we use the conformal definitions of a Gibbs measure. So now let's talk about these classical theorems. So we need first to restrict ourselves to when the group G is the set of integers. Subshift is irreducible if for every pair of patterns U and V, there is a pattern W such that UWV is allowed. And one characterization of a subshift being irreducible if it has doubly transitive points. A doubly transitive point is a point at every finite where W appears infinitely often to the left and to the right. And a stronger definition, we say that a subshift X is strongly irreducible if it is mixing. That is, if it is irreducible and aperiodic. Now, one proposition about the set of doubly transitive points that I just mentioned. So if X is in irreducible shift space and mu is a fully supported ergodic measure on X, then the set of doubly transitive points has measure 1. Now we are moving towards to introduce the definition of a Sohc shift. And for that, we need to define what a sliding block code is. So it's a map between two shift spaces that intertwines with the shift action, and such that pi of X at the coordinate 0 depends only on a central block of X. And when pi is surjective, we say that pi is actually a factor map, and a Sohc shift is nothing more than a factor of a shift of finite type. When X is a shift of finite type and Y is a Sohc shift, we say that the factor map pi is almost invertible if every doubly transitive point in Y has a unique preimage. So now I'm going to state the classical Dobrushin and Lanfrewell theorems with some adapted formulation. So the Dobrushin theorem says that if X is strongly irreducible and F is a potential with summable variation, then any shift invariant Gibbs measure is an equilibrium measure. And the Lanfrewell theorem says that if X is a shift of finite type and F is a potential with summable variation, then every equilibrium measure for F is a Gibbs measure for F. So for us to prove the Sohc versions of the Dobrushin and Lanfrewell theorems, we need some results of preservation of Gibbsianness. So the first one says that if X is an irreducible shift of finite type and Y is a Sohc shift, pi is an almost invertible factor code, and mu is a measure that is fully on X, that is fully supported, sigma invariant, ergodic, and Tx non-singular. Then if mu is a Gibbs measure with respect to a cocycle pi, then the push forward of the measure mu is also Gibbs with respect to this new cocycle. For us to prove that, some ideas, we use that the measure of the set of doubly transitive points on X is 1, that the image of the set of doubly transitive points on X is exactly the set of doubly transitive points on Y, and we lift holonomies from Y to X. The second result of preservation of Gibbsinness, we need X to be a shift of finite type, Y a Sohc shift, pi an almost invertible factor code, and nu now a measure on Y that is fully supported, sigma invariant, ergodic, and Ty non-singular. Then, if nu is a measure for a cocycle phi, then every sigma invariant measure mu on X such that nu is the push forward of mu is Tx non-singular, and in particular is a sigma invariant Gibbs measure for this cold cycle. And now the last result about preservation of something is a result about preservation of equilibrium states. So if again X is a shift of finite type and Y is a Sohc shift, pi is now a finite to one factor code, and F is a function with summable variation. Nu is an equilibrium measure for F, then there always exists an equilibrium measure mu for the composition of F and pi, such that nu is the push forward of mu. And if mu is ergodic, then mu can be chosen to be ergodic as well. Now, finally, the statement of the Dobrushin and Lanfrewell theorems for Sohc shifts. So we have Y an irreducible Sohc shift and F a potential with summable variation. Then nu is sigma, and nu is a sigma invariant Gibbs measure for F. Then nu is an equilibrium measure for F. And the Lanfrewell theorem, we have again an irreducible Sohc shift and F a potential with summable variation. Then any equilibrium measure for F is a Gibbs measure for F. For us to prove this result, we use a cover of these Sohc shifts, and we use the results of preservation of Gibbsinness and equilibrium measures for us to go from the Sohc shift to the SFT cover and go back to the Sohc shift. Thank you everyone for the attention.